The Big Bang was not an explosion, and it did not happen inside space, because there was no space yet for anything to explode into. Every point that would ever become a galaxy, a star, or the ground beneath your feet was once pressed into the same unimaginably small, unimaginably hot volume, and when that volume began to grow, it did not expand into some larger emptiness waiting outside it. It carried space and time along with it as it grew, stretching the distances between every point at once. This is the story of what actually happened in the first fractions of a second, the first few minutes, and the first several 100,000 years after that beginning, pieced together, not from guesswork, but from light still arriving, from the oldest thing we can see, and from elements still present in the stars overhead tonight. By the end, the phrase Big Bang should mean something different than it did a moment ago. In 1929, using a 100-inch telescope on a mountain outside Los Angeles, the American astronomer Edwin Hubble made a discovery that quietly rewrote humanity's picture of the universe. He had been measuring the light coming from dozens of distant galaxies, and he noticed something strange in nearly all of it. The light was shifted toward the red end of the spectrum, a phenomenon called redshift, meaning the light's wavelengths had been stretched to longer, redder values on their journey to Earth. Hubble found that the more distant a galaxy was, the more its light had been stretched, and the relationship between distance and stretching was almost perfectly linear. There was only one explanation that fit. The galaxies were not simply moving away from us through space. The space between us and them was itself growing. Hubble was not entirely working in the dark. 2 years earlier, a Belgian priest and physicist named Georges Lemaitre had worked out the mathematics of an expanding universe from Albert Einstein's equations of general relativity, and had predicted almost exactly the relationship Hubble went on to measure. Vesto Slipher, an American astronomer working a decade before either of them, had already measured redshifts in a handful of spiral nebulae without realizing what they implied. It took the combination of Lemaitre's theory and Hubble's systematic measurements to make the case impossible to ignore. The universe is not static. It is expanding, and it has been expanding for as long as it has existed. This single observation, stretched to its logical conclusion, leads somewhere startling. If every galaxy is moving away from every other galaxy today, then yesterday they must have been closer together, and the day before that, closer still. Run the clock back far enough, and everything we can see, every galaxy, every star, every atom, converges toward the same infinitesimally small point. That is the core insight behind what would later be nicknamed the Big Bang. A name coined somewhat dismissively in 1949 by the astronomer Fred Hoyle, who preferred a rival theory and never expected the phrase to stick. But the name misleads almost everyone who first hears it, because it conjures an image of a conventional explosion, a bomb going off at a single point in an already existing, empty space, with debris flying outward into the void. That picture is wrong in a fundamental way. There was no empty space waiting around the initial hot, dense state for it to explode into. Space itself is what was expanding, carrying the matter and energy within it along for the ride, the way the surface of a balloon carries dots painted on its skin as it inflates, or the way raisins in a loaf of bread pull apart from one another as the dough itself rises and swells in the oven. No raisin sits at the center of that loaf. Every raisin sees every other raisin moving away from it, and the ones farther away appear to move faster, exactly the pattern Hubble measured among the galaxies. There is no special vantage point, and critically, there was no center to the original expansion, because the expansion was not a spreading out from a point in space. It was, and still is, the growth of space itself. This distinction matters because it changes the question we are actually asking. We are not asking where the Big Bang happened, because it did not happen at a location we could point a telescope at and see more clearly. We are asking what a much smaller, much hotter, much denser universe was doing, everywhere, all at once, in its earliest moments. To answer that, astronomers and physicists have spent the better part of a century running Hubble's observation backward in time, using the known laws of physics to reconstruct, epoch by epoch, what the universe must have looked like as we rewind its expansion toward that first, almost unthinkably compressed instant. Rewinding an expanding universe is, in principle, straightforward arithmetic. If galaxies are moving apart at a rate we can measure today, then general relativity, the theory of gravity Einstein published in 1915, lets physicists calculate how dense and how hot the universe must have been at any earlier moment. Run the calculation back far enough, and the universe shrinks toward a state of almost incomprehensible density and temperature, everything that now fills a volume roughly 93 billion light-years across, compressed into a space many, many times smaller than a single atom. As that reconstructed universe gets smaller and hotter moment by moment, its behavior changes in ways we can describe with increasing confidence. 10 seconds after the beginning, the universe was cool enough that the physics involved is well understood and repeatedly confirmed by particle accelerators on Earth. 1 second after the beginning, it gets more exotic, but the relevant physics has still been tested. A tiny fraction of a second after the beginning, the required temperatures and densities move beyond anything a laboratory on Earth has ever produced, though the underlying particle physics is still built on principles we have verified in other contexts. Keep going backward, and eventually the reconstruction runs into a wall. That wall sits at a moment called the Planck time, roughly 10 to the negative 43 seconds after the start of the expansion, an interval so short that comparing it to a single second is roughly like comparing a second to the entire present age of the universe. Before the Planck time, the universe would have been so dense that gravity itself, which general relativity describes as the curving of space and time by mass and energy, would have needed to be unified with quantum mechanics, the theory that governs the behavior of particles at extremely small scales. Physicists do not yet have a complete, tested theory that combines the two. Approaches exist, string theory and loop quantum gravity among the most studied, and each makes different predictions about what might have preceded or constituted that earliest moment. None has yet been confirmed by an experiment, so an honest account has to stop at the edge of what current physics can responsibly claim and say plainly that the very first instant remains an open scientific question rather than a settled one. This is worth sitting with for a moment because it clarifies exactly what the Big Bang model does and does not claim. The model does not assert that scientists know what caused the universe to exist, or what, if anything, that came before it, or whether asking what came before even makes sense if time itself began at that moment. What the model does claim, and claims with a very high degree of confidence built from multiple independent lines of evidence, is that from an extremely early moment onward, roughly a trillionth of a second after whatever happened at the very start, the universe evolved through a definite calculable, testable sequence of stages, an extraordinarily rapid stretching, a hot soup of fundamental particles, the formation of the first atomic nuclei, and eventually the release of the ancient light we can still detect today. Each of those stages left a physical fingerprint that we can go looking for and have found. So the honest starting point for this story is not the absolute beginning, which remains unknown, but the earliest moment our physics can responsibly describe, an unimaginably hot, dense universe, already expanding, about to undergo the single strangest and most consequential event in its entire history, a burst of expansion so extreme that it would determine the large-scale shape of everything that followed. Sometime in the earliest sliver of the universe's history, likely beginning around 10 to the negative 36 seconds after the start, and ending by about 10 to the negative 32 seconds, most cosmologists believe the universe underwent a period of expansion unlike anything that happened before or since, a process called inflation. During inflation, the theory holds, the universe was dominated by an unusual form of energy, often described as an inflatoned field, that caused space to expand exponentially, doubling in size again and again at a staggering rate rather than expanding at the comparatively gentle pace we observe today. The scale of this stretching is difficult to put into ordinary language, but one comparison helps. If a single period at the end of a printed sentence were expanded by the same factor most inflation models require, roughly a factor of 10 to the 26 or more, it would grow larger than the entire presently observable universe, in a span of time far shorter than it takes a single beam of light to cross a proton. Whatever tiny region eventually became everything we can see, every galaxy, every star, every planet, was, before inflation, smaller than a single subatomic particle. Cosmologists did not propose inflation just because it sounds dramatic. It was introduced in 1980 by the physicist Alan Guth, and independently developed by others, including Andrei Linde and Alexei Starobinsky, specifically because it solves several puzzles that a simple non-inflating Big Bang model could not explain. One puzzle is the flatness problem. On the largest scales, the geometry of the universe appears extremely close to flat, meaning parallel light rays stay parallel rather than converging or diverging. and ordinary expansion without an inflationary burst would have needed an almost impossibly precise starting condition to end up looking this flat today. A period of extreme stretching naturally flattens out any initial curvature, in the same way that a huge balloon looks nearly flat from the perspective of an ant standing on its surface, even though the balloon as a whole is obviously curved. A second puzzle is the horizon problem. The cosmic microwave background, the ancient light we will examine closely a few chapters ahead, is almost perfectly uniform in temperature across the entire sky, varying by only a few parts in 100,000 between regions on opposite sides of the observable universe. Without inflation, those distant regions would never have been close enough together or existed long enough for light or any other signal to travel between them and even out their temperatures, which makes the observed uniformity difficult to explain. If space itself underwent an enormous stretching very early on, however, regions that are now impossibly far apart were, before inflation, close enough to interact and reach a common temperature, and inflation then carried them apart faster than light could ever have caught up again, freezing that uniformity in place. Inflation offers something else, something that turns out to matter enormously for everything that comes later in this story. Quantum mechanics tells us that even a field filling all of space is subject to tiny, random fluctuations, brief moment-to-moment variations in energy at scales far smaller than an atom. Inflation is thought to have taken those minuscule quantum fluctuations and stretched them, along with everything else, up to enormous cosmic size, freezing them into the fabric of the universe as extremely faint variations in density from one region to another. Those frozen ripples, astronomers now believe, became the seeds for every galaxy cluster, and every void in the cosmic web we observe today. Without that stretching, the universe that emerged when inflation ended would likely have been almost perfectly smooth and featureless, with nothing to eventually gather into stars. Instead, inflation appears to have ended by dumping an enormous amount of energy back into ordinary particles, reheating the universe to tremendous temperatures, and setting the stage for the next chapter in its story. When inflation came to an end, the energy that had driven that enormous stretching did not simply vanish. Most models hold that it converted almost entirely into ordinary particles and radiation, an event called reheating, which filled the newly enlarged universe with an extraordinarily hot, dense soup at a temperature that some estimates place as high as 10 to the 27 degrees, a figure so extreme it has little intuitive meaning beyond the fact that it dwarfs anything ever produced in a laboratory or observed in the core of any star. At these temperatures, the universe was not made of atoms, or even of the protons and neutrons that would eventually build atoms. It was a churning bath of fundamental particles, quarks, electrons, neutrinos, and their less familiar cousins, along with an equal number of their antiparticles, matter's mirror image counterparts that carry the opposite electric charge, but the same mass. Photons, particles of light, so numerous and so energetic that they constantly collided with particles and antiparticles, creating and destroying pairs of them in a continuous frantic exchange. Nothing resembling a stable structure could exist yet. There was no time for it. Particles collided, annihilated, and reformed far too rapidly. At these energies, physicists believe the fundamental forces of nature behaved very differently than they do in today's cooler universe. We currently recognize 4 fundamental forces: gravity, which shapes the large-scale structure of the cosmos; electromagnetism, which governs light and the behavior of charged particles; the strong force, which binds quarks together inside protons and neutrons; and the weak force, which governs certain kinds of radioactive decay. At sufficiently high energies, the electromagnetic and weak forces are believed to unify into a single electro-weak force, a merger that has actually been confirmed experimentally at particle accelerators such as CERN's Large Hadron Collider, which can recreate in miniature energy conditions similar to those present roughly a trillionth of a second after the beginning. Some theories go further, proposing that at even higher, currently untestable energies, the strong force joins the unified electroweak force in what is called a grand unified theory, and that gravity itself may unify with the rest at energies approaching the Planck scale discussed earlier. These further unifications remain hypotheses, actively researched but not yet confirmed, and any honest account keeps that distinction clear. As the universe continued to expand and cool, following the same relationship between size and temperature that governs it today, the forces that had been unified at extreme energies began to separate, or in physics language, to break their symmetry, becoming the four distinct forces we observe now. This is thought to have included a genuinely dramatic transition called electroweak symmetry breaking, occurring around 1/10 billionth of a second after the beginning, during which particles are believed to have acquired mass through an interaction with the Higgs field, the same field whose associated particle, the Higgs boson, was finally detected experimentally at CERN in 2012, decades after it was first proposed. This period, brief as it was on any everyday clock, but containing an enormous amount of physical change, laid the groundwork for the particles and forces that would go on to build everything else. Yet one deep puzzle from this era remains genuinely unsolved. Physics predicts that matter and antimatter should have been created in exactly equal amounts during this hot phase, and should therefore have annihilated each other almost completely, leaving behind a universe of pure light with essentially no matter at all. Something tipped that balance, leaving a tiny surplus of matter, roughly one extra particle for every billion or so matched pairs, and that tiny surplus is the entire reason there is a physical universe of stars, planets, and people today rather than an empty bath of photons. What caused that imbalance is one of the open questions cosmologists and particle physicists are still actively investigating, and the next stage of the story depends entirely on that small surviving surplus. Carrying forward that tiny surviving surplus of matter over antimatter, the universe continued expanding and cooling, and by roughly 1 microsecond, 1/1,000,000th of a second, after the beginning, it crossed a threshold that physicists call the quark-hadron transition. Before this moment, quarks, the fundamental particles that make up protons and neutrons, existed in a free-roaming state called a quark-gluon plasma, moving individually through the hot, dense medium rather than being bound together. Gluons, the particles that carry the strong force, held this plasma together as a kind of heated soup, one that physicists have actually recreated for brief instants inside heavy ion colliders on Earth, confirming that it behaves the way theory predicts. As the temperature dropped below a critical value, the strong force, which grows stronger rather than weaker as quarks try to separate, finally succeeded in locking quarks permanently into tightly bound triplets. Two types of these triplets mattered most for everything that followed. Combinations of 2 up quarks and 1 down quark formed protons, and combinations of 1 up quark and 2 down quarks formed neutrons. From this point onward, free individual quarks essentially ceased to exist in the universe at large. They have remained locked inside protons, neutrons, and a handful of more exotic, short-lived particles ever since, a confinement so complete that no isolated quark has ever been directly observed. Because of the earlier matter-antimatter imbalance, protons and neutrons were now slightly more numerous than their antimatter counterparts, antiprotons and antineutrons. As the universe continued to cool, matter and antimatter particles collided and annihilated each other in overwhelming numbers, converting back into photons of light. Almost all of the antimatter was destroyed this way, along with almost all of the matter, but that tiny original surplus meant a small residue of ordinary protons and neutrons survived the annihilation alongside an enormous number of photons. Today, for roughly every 1 billion photons of light, the observable universe contains only about 1 proton or neutron, a ratio that traces directly back to that ancient imbalance. At the same time, another population of particles was decoupling from the rest of the hot soup. Neutrinos, extremely light, weakly interacting particles that barely interact with ordinary matter at all. Around 1 second after the beginning, the universe had thinned out enough that neutrinos stopped colliding frequently with other particles and began streaming freely through space, essentially unimpeded, a state they remain in today. This relic neutrino background, sometimes called the cosmic neutrino background, is predicted by the same physics that predicts the more famous cosmic microwave background discussed later in this story, though it has never been directly detected, since neutrinos interact so weakly that even a light year of solid lead would stop only about half of them passing through. With protons and neutrons now locked in and stable, and neutrinos freely streaming, the universe had, in the span of a single second, gone from a free-roaming plasma of exotic particles to something built from the same basic ingredients that make up ordinary atomic nuclei today. But protons and neutrons alone are not yet atoms, and they had not yet combined with one another into anything more complex. That transformation, the forging of the first atomic nuclei from these newly stabilized particles, was about to begin, and it would happen with a speed and a precision that scientists can now calculate and verify against what we actually observe in the composition of stars. For roughly the first 3 minutes after the beginning, the universe was too hot for protons and neutrons to stay bound together even when they collided. Any nucleus that briefly formed was instantly blasted apart by the intense radiation surrounding it, but as the temperature kept falling with the ongoing expansion, it eventually dropped low enough to around 1 billion degrees that fusion could finally stick. Between roughly 3 and 20 minutes after the beginning, in a process called Big Bang nucleosynthesis, protons and neutrons began fusing together to build the very first atomic nuclei in the history of the universe. The process moved with remarkable speed, and it produced remarkably little variety. A proton and a neutron first combined to form deuterium, sometimes called heavy hydrogen, a nucleus with one proton and one neutron rather than hydrogen's usual lone proton. Deuterium nuclei then rapidly fused further, mostly into helium-4, a stable nucleus with 2 protons and 2 neutrons. A small amount of an even rarer isotope, helium-3, and a trace of lithium-7, the third lightest element, also formed. Almost nothing heavier formed at all, because the necessary intermediate nuclei were unstable, and the universe was expanding and cooling too quickly to bridge the gap before conditions changed again. Within about 20 minutes, the temperature had dropped too low for any further fusion, and the process simply shut off. The result was a universe whose ordinary matter by mass was roughly 75% hydrogen and about 25% helium, with only faint traces of lithium and nothing heavier, no carbon, no oxygen, no iron, none of the elements that would later make up rocky planets or living things. This predicted ratio is one of the most precisely tested claims in all of cosmology. Astronomers can measure the actual helium and lithium content of the oldest, most pristine gas clouds and the most ancient stars they can find, environments barely touched by the element building that happens inside stars, and the observed ratios match the Big Bang nucleosynthesis prediction closely enough that this agreement stands as one of the strongest pieces of evidence for the entire Big Bang framework. Here is a way to make that number feel less abstract. Roughly 1 in every 4 hydrogen nuclei that existed just before this process began was consumed to make helium instead, meaning that a full quarter of the ordinary matter later spread across every galaxy in the sky. The matter that would eventually make up stars, planets, and the atoms in your own body had its basic identity settled within the first 20 minutes of the universe's existence, faster than it takes to boil an egg. Everything heavier than lithium that exists today, the carbon in every living thing, the oxygen we breathe, the iron in blood and in planetary cores, the silicon in rock and sand, was made much later, inside the cores of stars and in the violent deaths of the largest of them, a process the story of a star's life and death traces in its own right. But this early universe, cooling rapidly after its first burst of nuclear fusion, was still nowhere near finished changing. It remained a hot, dense, glowing plasma, and light itself was still trapped inside it, unable to travel freely. That trapped light and the extraordinarily long wait before it could finally escape is where this story turns next. With the first atomic nuclei forged, one might expect atoms to have formed almost immediately, since a hydrogen nucleus is just a proton waiting to capture an electron, and helium nuclei needed only 2. But that capture could not happen yet, and the reason has to do with just how hot the universe still was. At temperatures above a few thousand degrees, any electron that briefly attached itself to a nucleus was almost instantly knocked loose again by a collision with a high-energy photon. So even though the raw ingredients, protons, helium nuclei, and free electrons, were all present in the right proportions, they could not settle into stable neutral atoms. Instead, the universe remained a plasma, an ionized gas of charged particles and free electrons, for hundreds of thousands of years. This plasma had a profound consequence for light itself. A photon travelling through a sea of free electrons cannot travel far before it collides with one, a process called Thomson scattering, which knocks the photon off in a new, essentially random direction. Imagine trying to see through a thick, swirling fog. Light does not travel in a straight line through fog. It bounces from droplet to droplet until it eventually reaches your eye from an unpredictable direction, which is why fog appears as a uniform glow rather than letting you see clearly through it to whatever lies beyond. The early universe behaved the same way, except the fog was made of free electrons rather than water droplets, and it filled the entire universe rather than a stretch of highway. No photon could travel far. or in a consistent direction for as long as free electrons remained abundant, which meant the universe as a whole was opaque. If a person could somehow have existed then and looked outward in any direction, they would have seen only a featureless glowing haze, with no way to make out any individual object at any distance, because light itself had not yet been given the freedom to simply go somewhere and arrive intact. This era is sometimes called the radiation-dominated era, because photons and the tightly coupled electrons and protons they constantly interacted with dominated the universe's total energy content, rather than the ordinary matter that would later dominate, or the mysterious dark energy that dominates the universe today. During this stretch, the universe was expanding and cooling, but the plasma remained close to a smooth, even thermal equilibrium, meaning most regions of it stayed at nearly the same temperature and density as their neighbours. Aside from those extremely faint variations, the frozen ripples inflation had stretched into the fabric of space many chapters earlier. Those tiny variations mattered enormously even during this opaque period, because they meant the plasma was not perfectly still. Regions that were very slightly denser than average pulled in matter gravitationally, while the intense pressure of trapped radiation pushed back outward, setting up a kind of oscillation, matter falling in, radiation pushing back out, over and over, creating rippling pressure waves that moved through the plasma similar to sound waves moving through air. These are called baryon acoustic oscillations, and remarkably, the characteristic size of those ancient sound waves, frozen in place at the moment this era finally ended, can still be measured today in the spacing between galaxies across enormous stretches of the observable universe, functioning as a kind of cosmic ruler that helps confirm the whole model. But the fog could not last forever. As the universe kept expanding, its temperature kept falling, and it was only a matter of time before conditions changed enough for electrons to finally find a nucleus they could hold onto for good, a change that would, in a single relatively brief cosmic moment, let the fog lift and let light finally travel freely for the first time. Roughly 380,000 years after the beginning, the universe's temperature had fallen to around 3,000 degrees, cool enough that free electrons could finally, permanently, bind to atomic nuclei without being immediately knocked loose again. Hydrogen nuclei captured electrons to become neutral hydrogen atoms. Helium nuclei captured electrons to become neutral helium atoms. This transition is called recombination, a slightly misleading name since electrons and nuclei were combining for the first time. Not recombining, but the name has stuck since it was first used. Recombination did not happen everywhere in a single instant. It unfolded relatively quickly but not instantaneously, over a span of roughly 100,000 years as different regions of the universe crossed the necessary temperature threshold. But cosmologically speaking, this was an abrupt and transformative event. As free electrons rapidly disappeared, bound up inside newly neutral atoms, the fog that had scattered light for the universe's entire previous history simply lifted. Photons that had spent 380,000 years bouncing helplessly from electron to electron suddenly found themselves with nothing left to scatter off of. They began travelling in straight lines, uninterrupted. For the first time in the universe's history, and in most cases, they have continued travelling in a straight line ever since. That light is still out there, and remarkably, we can still detect it. As the universe continued to expand over the following 13.8 billion years, the wavelength of that ancient light stretched along with the space it was travelling through, the same redshift effect that let Hubble measure the universe's expansion, except carried to an extreme degree. Light that started out as a searing, brilliant orange-white glow at 3,000 degrees has been stretched by the universe's expansion into microwave wavelengths, cold radiation corresponding to a temperature of just 2.7 degrees above absolute zero. This is the cosmic microwave background, often abbreviated CMB, and it was discovered largely by accident in 1965 by two Bell Labs radio engineers, Arno Penzias and Robert Wilson, who were troubleshooting unexplained background noise in a radio antenna, and eventually realized they were detecting the afterglow of the early universe itself. The cosmic microwave background is, in a very real sense, a photograph of the universe at the exact moment it became transparent. It arrives from every direction in the sky, essentially uniform in temperature to a precision of better than 1 part in 100,000, but not perfectly uniform. Satellites built specifically to map it in exquisite detail, COBE in the late 1980s, WMAP in the 2000s, and the European Planck satellite in the 2010s have revealed a faint mottled pattern of slightly hotter and slightly cooler spots across the sky, corresponding directly to those tiny density variations that inflation stretched into existence in the universe's first fraction of a second, and that later grew, through gravity, into every galaxy and galaxy cluster that exists today. So when a viewer looks at a map of the cosmic microwave background, they are looking at the oldest light that will ever reach any telescope, a fossil imprint of an event that happened 13.8 billion years ago, everywhere in the universe all at once. Beyond it, in every direction, lies the era before recombination, the opaque plasma this story has just walked through, forever hidden from direct observation by light's own inability to escape it. But after recombination, with the fog finally lifted, the universe entered a strange new phase, transparent but almost entirely dark, because the atoms that had just formed had nothing yet to light them from within. Immediately after recombination, the universe entered what astronomers call the cosmic dark ages, a period that likely lasted somewhere between 100 million and 200 million years, though the exact boundary remains an active area of research. The name fits literally, with electrons now bound into neutral hydrogen and helium atoms, and with no stars yet in existence to produce new light. There was essentially no visible light anywhere in the universe. The cosmic microwave background continued to fill space, but that glow was fading and redshifting toward invisibility as the universe expanded, and nothing had yet replaced it as a source of illumination. The universe during this period was not empty or featureless, however. It was filled with a vast, mostly uniform sea of neutral hydrogen gas, along with helium and a still mysterious substance called dark matter, an invisible form of matter that does not emit, absorb, or reflect light of any kind, but which we know exists because of its gravitational effects on visible matter and on light itself. Dark matter is believed to make up roughly 5 times as much mass in the universe as ordinary atomic matter, and though its exact particle nature remains one of the biggest unanswered questions in physics, its gravitational role during the Dark Ages was decisive. Recall those tiny density variations frozen into the universe by inflation, the ones later mapped in exquisite detail on the cosmic microwave background. During the Dark Ages, gravity got to work on those variations in earnest. Regions that started out very slightly denser than average, whether in ordinary matter or more importantly in dark matter, attracted more matter toward themselves over time, growing denser still, while regions that started out slightly less dense became progressively emptier as matter drained away from them. Because dark matter interacts with almost nothing except gravity, it was free to begin clumping together immediately after inflation's ripples were laid down, well before recombination even happened, forming an invisible scaffolding of gravitational wells. Ordinary hydrogen and helium gas, once freed from the pressure of trapped radiation at recombination, began falling into these dark matter wells, slowly concentrating into denser and denser clouds. To put the timescale in human terms, imagine the entire 13.8 billion year history of the universe compressed into a single 24-hour day. On that scale, the Big Bang happens at midnight, and recombination, the moment the fog lifted, happens only about 2.5 seconds later. The Dark Ages that follow, though they felt to the universe like a genuinely long stretch of cosmic time, occupy barely more than 1 additional second on that same clock, a brief hush before anything happens, but a hush during which gravity was quietly doing an enormous amount of unseen work. Eventually, in the densest of these slowly collapsing clouds of hydrogen and helium, gravity's pull became strong enough to compress the gas at the cloud's center to extraordinary densities and temperatures, hot enough, at roughly 10 million degrees, to ignite nuclear fusion. When that happened, for the very first time since the universe's original burst of nucleosynthesis in its first 20 minutes, new light began to shine, not from the cooling afterglow of the beginning, but from a star, and the long, dark hush of the cosmic dark ages was about to end. The first stars to ignite in the universe, sometime around 100 million to 250 million years after the beginning, according to current models, were unlike almost any star that exists today. Astronomers call this hypothesized first-generation population 3 stars, a name that reflects an odd historical numbering convention rather than any obvious sequence, and none has yet been directly observed, since they are believed to have been extremely short-lived and to have existed only in the extremely distant, hard-to-observe early universe. Their properties are inferred from theoretical models and from indirect evidence, So this chapter's account carries a somewhat higher degree of uncertainty than the nuclear physics discussed earlier, and current research treats several details as still unsettled. What made these first stars so different from the Sun and its contemporaries comes down to composition. Every star that has ever formed since, including the Sun, condensed from clouds of gas already enriched with elements heavier than helium, elements astronomers collectively and somewhat confusingly call metals, that were produced by earlier generations of stars and scattered into space when those stars died. The very first stars had no such enrichment to draw on. They formed from gas that was, as established a few chapters back, essentially only hydrogen and helium, with barely a trace of lithium and nothing heavier at all. This absence of heavier elements changed how these clouds collapsed and cooled. Heavier elements are efficient at radiating away heat, which lets a collapsing gas cloud cool and fragment into many smaller clumps, ultimately producing stars across a wide range of sizes, much like star formation happens today. Without that cooling assistance, the first collapsing clouds are thought to have fragmented far less, producing far fewer but far more massive individual stars. Some models suggest many were hundreds of times the mass of the Sun, extraordinarily large compared to the Sun's own size, which is itself roughly 100 times wider than Earth. Stars that massive burn through their nuclear fuel at a ferocious rate and live extremely short lives by stellar standards, likely only a few million years compared to the roughly 10 billion years the Sun is expected to shine. When they exhausted their fuel, current models predict they died in extremely energetic supernova explosions, or in some cases may have collapsed directly into black holes without an explosion at all, and either way, they scattered the first heavier elements the universe had ever produced, carbon, oxygen and others forged inside their brief, furious lives, out into the surrounding gas, seeding it for the next generation of star formation. These first stars did something else, something with consequences for the entire universe rather than just their immediate surroundings. Being so massive and so hot, they radiated enormous amounts of ultraviolet light, energetic enough to knock electrons back off the neutral hydrogen atoms that filled the space around them, a process called ionization. Each of these earliest stars carved out a growing bubble of ionized, once again electrically charged, gas around itself, pushing back against the vast surrounding sea of neutral hydrogen that had filled the universe since recombination. Individually, these bubbles were small compared to the whole universe, but as more and more stars, and eventually entire early galaxies, formed and ignited over the following hundreds of millions of years, those bubbles began to grow, merge and spread, setting in motion a slow, universe-wide transformation that would eventually leave almost no neutral hydrogen fog left at all. The bubbles of ionized gas carved out by the first stars continued to grow through what astronomers call the epoch of reionization, a gradual, patchy process that current evidence suggests was largely complete by around 1 billion years after the beginning, though its precise start and end dates remain an active area of observational research, with different lines of evidence pointing to somewhat different timings. As more first-generation stars ignited, and as gravity continued pulling matter together into the earliest small galaxies, the total amount of ionizing ultraviolet light flooding the universe increased dramatically, and the individual bubbles of ionized hydrogen around each source began to overlap and merge with their neighbors. This was not a smooth, even process happening at the same pace everywhere. Regions of the universe that had collapsed earliest and most densely, thanks to the same dark matter scaffolding discussed a couple of chapters back, tended to form stars and galaxies earliest, and so those regions reionized first, while other less dense regions lagged behind, remaining neutral and opaque to ultraviolet light for longer. Astronomers studying reionization sometimes describe the universe during this transitional period as looking like Swiss cheese, with growing ionized bubbles carved out of a still mostly neutral background, though this comparison is meant only to describe the uneven, patchy geometry, not the composition of anything actually present. Galaxies themselves were assembling rapidly during this period, as gravity pulled ever more gas and dark matter together into larger, more organized structures. The very earliest galaxies were likely small, chaotic, and irregular compared to the large, well-organized spiral and elliptical galaxies familiar from images of the nearby universe today, but they grew both by pulling in fresh gas and by merging with neighboring smaller galaxies, a process of hierarchical assembly that current models suggest continued, in a gentler form, for billions of years afterward. Some of the largest of these early galaxies developed enormous, rapidly growing black holes at their centers, and material spiraling into those black holes heated up and radiated intensely before crossing the point of no return, producing extraordinarily luminous objects called quasars, some of the brightest single objects in the entire universe, whose light added substantially to the ultraviolet radiation driving reionization forward. By the time reionization was essentially complete, roughly a billion years after the beginning, the universe had undergone its second great transparency transition. The first, recombination, had let visible and infrared light finally travel freely through space, ending the primordial fog of free electrons. This second transition let ultraviolet light travel freely as well, since there was almost no neutral hydrogen left to absorb it, aside from small, dense pockets that still exist today inside and around individual galaxies. Astronomers can actually observe evidence of the tail end of this transition directly, by studying the light from extremely distant quasars. Light from quasars observed at the very edge of the reionization era shows distinctive absorption features caused by intervening patches of neutral hydrogen gas that had not yet been ionized, a phenomenon called the Gunn-Peterson trough, while light from quasars slightly closer to us, corresponding to a slightly later cosmic time, does not show this absorption at all, marking the observational boundary of reionization completion. With the universe now transparent across almost the entire electromagnetic spectrum, and with galaxies increasingly assembled into organized structures, the stage was set for gravity to keep doing what it had been doing quietly since the very earliest moments after inflation, pulling matter together on ever larger scales into the vast, intricate structure that astronomers now map across billions of light-years of space. Over the roughly 13 billion years since reionization, gravity has continued the process it began quietly during the Dark Ages, gathering matter into progressively larger and more organized structures. But the pattern that has emerged is not a uniform scattering of galaxies evenly spread through space, the way salt might be evenly shaken across a table. Large-scale surveys that map the positions of hundreds of thousands of galaxies across enormous volumes of the observable universe reveal something far stranger and more structured. Galaxies are arranged along vast, thread-like filaments, some stretching hundreds of millions of light-years in length, which connect at dense knots called galaxy clusters, while enormous, comparatively empty regions called voids, some also hundreds of millions of light-years across, occupy the spaces between the filaments. Astronomers collectively call this arrangement the cosmic web. The cosmic web did not arise from ordinary matter alone. Dark matter did most of the initial structural work, for the same reason it did during the Dark Ages. Because dark matter barely interacts with anything except through gravity, it began clumping around the tiny density fluctuations. Inflation had frozen into the universe far earlier and far more efficiently than ordinary matter could, since ordinary matter's clumping was slowed by radiation pressure until recombination released it. By the time recombination occurred, dark matter had already built up a faint invisible skeleton of denser and less dense regions spanning the observable universe, and ordinary gas, once freed from radiation pressure, simply fell into the gravitational wells that skeleton provided, tracing out in visible light and visible galaxies a structure that dark matter had already sketched out first. Within the densest knots of this web, where multiple filaments converge, galaxies fell together and merged repeatedly over billions of years, building the largest bound structures in the universe, galaxy clusters, which can contain anywhere from a few hundred to several thousand individual galaxies, all held together by their combined gravity, along with an enormous amount of superheated gas glowing in X-rays, and of course, an even larger amount of dark matter. Our own galaxy, the Milky Way, sits within a much smaller, looser grouping called the Local Group, alongside the Andromeda Galaxy and dozens of smaller companions, itself just one small node within the much larger Laniakea supercluster, a name that means immense heaven in Hawaiian, chosen by the astronomers who mapped its boundaries in 2014. To get a feel for the scale of these filaments, consider that a beam of light, which crosses the roughly 150 million kilometers between the Sun and Earth in about 8 minutes, would take hundreds of millions of years to travel the length of one of the cosmic web's larger filaments, longer than most of the entire history of complex life on Earth. And yet, on the very largest scales, averaged over distances even greater than a filament's own length, the universe looks remarkably smooth and statistically uniform in every direction, a property called large-scale homogeneity that is itself one of the founding assumptions modern cosmological models rely on, and that observations have repeatedly confirmed. This vast, web-like architecture, built from a combination of ordinary matter, invisible dark matter, and a history stretching back to the faintest density ripples inflation stamped into the universe in its first fraction of a second, is the large-scale structure astronomers now study using enormous painstaking surveys and increasingly powerful telescopes. But mapping where galaxies are is only part of the picture. To fully test the model this entire story has traced, cosmologists also needed to measure, with far greater precision than Hubble's original 1929 estimate, exactly how fast the universe is expanding today, and how that expansion rate has changed over cosmic time, a project that would eventually turn up one of the biggest surprises in the whole field. Hubble's original 1929 measurements were groundbreaking, but they were also rough, based on a relatively small number of galaxies and distance estimates that later turned out to contain significant errors. Refining that first crude estimate of the universe's expansion rate, a number astronomers call the Hubble constant, into something precise enough to test detailed cosmological models of 20th and 21st astronomy. Of 20th and 21st century astronomy. That refinement came from several independent directions at once, and the fact that they largely agree with one another is itself powerful evidence for the underlying model. One approach uses what astronomers call standard candles, objects whose true brightness can be worked out independently of how bright they appear from Earth. Most importantly, a specific class of exploding star called a Type Ia supernova, which reaches a strikingly consistent peak brightness across the vast majority of observed cases, letting astronomers calculate its distance by comparing that known true brightness to how faint it appears. A second, entirely different approach studies the cosmic microwave background itself, extracting the universe's expansion history, its geometry, its age, and its composition from the precise pattern of hot and cold spots mapped by satellites including COBE WMAP and the European Space Agency's Planck satellite, launched in 2009 and operating until 2013, whose final full-sky maps remain among the most precise cosmological datasets ever produced. Taken together, these and other independent lines of evidence converge on what cosmologists now call the standard model of cosmology, sometimes referred to by the technical shorthand lambda CDM, a name built from the mathematical symbol for dark energy and the term cold dark matter. This standard model puts the age of the universe at 13.8 billion years, accurate, according to the Planck satellite's data, to within roughly 20 million years either way, an extraordinary degree of precision for a measurement spanning the entire history of everything. The same model indicates that ordinary atomic matter, the stuff of stars, planets, and people, makes up only about 5% of the universe's total energy content, while dark matter makes up roughly 27%, and the remaining 68% or so belongs to a mysterious component called dark energy, which the next chapter takes up directly. One genuine unresolved puzzle has emerged from this precision measurement project, and an honest account has to include it. The value of the Hubble constant measured using nearby Type Ia supernovae and other local distance ladder techniques consistently comes out a few percent higher than the value inferred from the cosmic microwave background's ancient light, a discrepancy researchers call the Hubble tension. The gap is small in absolute terms, but it is larger than the known measurement uncertainties on either side would predict, which means either some subtle, uncorrected error remains hidden in one or both measurement techniques, or, more intriguingly, the standard cosmological model is missing some piece of new physics not yet accounted for. Cosmologists are still actively working to resolve this tension, and it stands, at the time of this recording, as one of the most closely watched open questions in the field. Even with that tension unresolved, the broader model built from these measurements, an expanding universe roughly 13.8 billion years old, dominated by dark matter and dark energy, with ordinary matter as a comparatively minor ingredient, is supported by an enormous, independently cross-checked body of evidence. And it was precisely this kind of careful, precise measurement project that stumbled onto one of the strangest discoveries in the entire history of cosmology. The universe's expansion, rather than gradually slowing down under its own gravity, as everyone had assumed it must, is actually speeding up. Through most of the 20th century, cosmologists assumed that the universe's expansion, whatever its exact rate, must be gradually slowing down over time. This assumption followed directly from gravity. Every bit of matter in the universe pulls gravitationally on every other bit, and that mutual attraction should act as a brake on the expansion, slowly reducing its speed the way gravity pulls a ball thrown into the air back down toward Earth. The only real question, as far as most researchers were concerned heading into the 1990s, was how quickly the expansion was decelerating, and whether that deceleration would eventually stop the expansion entirely and cause the universe to collapse back in on itself, or merely slow toward a gentle eternal coast. Two independent research teams set out in the 1990s to measure that deceleration directly, using distant Type Ia supernovae as the same kind of standard candles discussed in the previous chapter, comparing how bright these exploding stars appeared at various distances, and therefore at various points back in cosmic time, to how bright a purely decelerating expansion model predicted they should appear. One team was led by Saul Perlmutter, the other by Brian Schmidt and Adam Rias. In 1998, both teams announced results that stunned much of the astronomical community, results confirmed and refined many times since. The most distant supernovae were fainter than a decelerating universe predicted they should be, meaning they were farther away than expected, which meant the universe's expansion was not slowing down at all. It was speeding up. The three scientists shared the 2011 Nobel Prize in Physics for the discovery. An accelerating expansion requires some kind of repulsive influence strong enough to overcome gravity's pull on the largest scales, and cosmologists gave this unknown influence a deliberately provisional name, dark energy. The name is, in an important sense, a placeholder for something not yet understood, rather than a description of a known physical mechanism, and any account that presents dark energy as a settled, well-explained phenomenon is overstating the science. What is well established from the supernova evidence, and independently confirmed by the CMB measurements and large-scale structure surveys discussed in the previous chapter, is that roughly 68% of the universe's total energy content behaves as if it exerts a repulsive gravitational effect on cosmic scales, and that its influence has caused the expansion rate to shift from slowing down to speeding up starting roughly 5 billion years ago, as matter thinned out enough for dark energy's relatively constant push to finally overtake gravity's now weakened pull. The leading candidate explanation treats dark energy as a property of empty space itself, called the cosmological constant, an idea Einstein actually introduced decades earlier, in 1917 for entirely different reasons, then reportedly called his greatest blunder after Hubble's discovery of expansion made it seem unnecessary, only for something remarkably similar to reappear as the leading explanation for acceleration 8 decades later. Under this interpretation, every cubic meter of truly empty space carries an unchanging tiny amount of energy that pushes space to expand faster as more space comes into existence, and more space always contributes more of this push, which is why its effect only came to dominate once matter, whose gravitational pull weakens as it spreads out, thinned out enough to lose the tug-of-war. Other researchers propose more exotic alternatives, some form of dynamic energy field that changes over cosmic time rather than staying constant, or, in a smaller number of proposals, a modification to general relativity itself on the largest scales rather than a new form of energy at all. None of these alternatives currently has decisive observational support over the others, and resolving what dark energy actually is remains one of the central open problems in modern physics. Whatever dark energy ultimately turns out to be, its discovery in 1998 completed the modern picture of cosmic history this story has traced from the earliest describable instant onward. An inflationary burst, a hot particle soup, the forging of the first light elements, a long opaque fog, its sudden lifting into the light we still see today as the cosmic microwave background, a dark hush before the first stars, the slow burning away of the primordial hydrogen fog, the patient gravitational construction of the cosmic web, and finally, an expansion that spent its first 9 billion years decelerating under matter's pull, before spending its most recent 5 billion years accelerating under an influence we still cannot fully name. Return for a moment to the misconception this story opened by correcting. The Big Bang was not a bomb going off at a point inside a pre-existing empty space, scattering debris outward into a void that was already there waiting for it. It was, and remains, a description of what an unimaginably hot, dense state of the entire universe was doing, at every point, all at once, as space itself began stretching and has continued stretching ever since. There was no center to that stretching, in the same way no single raisin sits at the center of a rising loaf of bread, and there is no edge to it either, no boundary out past the farthest galaxy, where the universe simply stops and something else, or nothing at all, begins. As far as every measurement made so far can tell, the universe is, on its largest observable scales, remarkably close to spatially flat and apparently without any edge, though whether it is truly infinite in extent, or merely far larger than the roughly 93 billion light-year sphere we can currently observe, remains an open question current data cannot yet settle. Every stage of the story this episode has traced left a fingerprint we can still detect. The relative abundance of hydrogen, helium, and lithium in the oldest stars confirms what happened in the universe's first 20 minutes. The cosmic microwave background, the ancient light released when the universe first turned transparent 380,000 years later, still arrives from every direction in the sky, carrying in its faint mottled pattern the frozen imprint of quantum fluctuation stretched to cosmic size by inflation in the very first fraction of a second. The measured abundance and distribution of dark matter, the observed acceleration of the expansion, and the large-scale filaments and voids of the cosmic web all fit together into a single coherent, testable, repeatedly confirmed account, even though several genuinely important pieces, what dark matter and dark energy actually are, what happened before the earliest instant our physics can describe, and why the Hubble tension persists, remain honestly unresolved. Those remaining gaps are not a weakness to apologize for. They mark exactly where current research is aimed, and cosmology has a long history of turning its open questions into settled answers within a generation or two. The expansion of the universe itself was an open, disputed question less than a century ago, and the cosmic microwave background was entirely unknown until an accidental discovery in a radio antenna in 1965. Whatever answers eventually resolve today's open questions will almost certainly come from the same combination of careful observation and testable theory that built every stage of the story told here. Hold a single grain of sand at arm's length against a dark, moonless patch of night sky. It covers only a tiny sliver of the sky's total area. Point a sufficiently powerful telescope at that same tiny patch and expose the image for hours or days rather than a fraction of a second, as astronomers have done repeatedly, most famously with the Hubble Space Telescope's deep field images beginning in 1995, and that seemingly empty sliver resolves into thousands of individual galaxies, each one containing hundreds of billions of stars, each one the product of the same 13.8 billion year history. An inflationary stretch, a forging of light elements, a long fog and its lifting, a dark hush, a first ignition of starlight, and a slow, patient, ongoing gravitational assembly into everything we can now see. That grain of sand's worth of sky is a fair sample of the whole. Multiply it across the entire visible dome above you, and you are looking, whether you can see it directly or not, at the unfolding result of the single most consequential fraction of a second in the history of everything that exists. Look up on a clear night and every point of light you can see, and every point too faint or too far to see, sits inside the same expanding fabric that began 13.8 billion years ago, in a state almost too hot and dense to describe. There was no center to that beginning, and there is no center to the universe today, in the same way that no single raisin sits at the center of a rising loaf of bread. There was no edge for the expansion to press against, and as far as our best instruments can tell, there still is not one. What we call the Big Bang is not a location and not an event that happened somewhere else. It is a description of what every location was doing, everywhere at once, at the start of time as we understand it. The faint microwave glow that fills the whole sky is the oldest light we will ever see, a fossil of the moment the universe first became transparent, and the elements in your body were forged either in the universe's first few minutes or in the cores of stars that lived and died long before the sun existed. A single grain of sand held at arm's length against a dark patch of sky, magnified by a deep enough exposure, resolves into thousands of galaxies, each one an assembly of hundreds of billions of stars, each one a product of the same stretching, cooling, clumping history this episode has traced. We do not yet know what, if anything, came before the earliest instant our physics can describe, and any honest account says so plainly. What we do know is that the universe we live inside is not a finished static backdrop. It is a process still unfolding, and we are, for a brief cosmic moment, watching a small part of it happen.